All right, so in this section, we're going to talk about trig powers. And you've probably had a little bit of exposure to some of these things, be it informally or formally, but either way, you'll start to quickly pick up on how things can get a little bit more in-depth with these powers. So the first thing I want to look at here is just a basic integral of cosine squared of x dx. Now remember, you can't really do much with cosine squared as it sits, and so what we would do here is use one of our trig identities. And so the appropriate identity, the one that would actually allow us to integrate, would be the 1 plus cosine 2x dx over 2. And from there, you can do it a number of ways. You can take the 1/2 and pull it out and integrate term by term, or you can split it up like this, which is probably the most direct way of doing this. So we've got our cosine 2x dx. And so that first term would be a 1/2 x, and that second term would give us a plus 1/4 sine 2x plus c. Okay, and integrating this, again, it's just a u sub, let u equal the inside, then the du would be the 2 dx, divide that off, that's where the 1/4 comes from, the integral of cosine is sine. So there you go on that one. And then similar, which I do think is worth our time mentioning, would be the integral for sine squared of x dx. The identity that you would use is similar. It would be a 1 minus cosine 2x over 2 dx. I would split this one up in a pretty similar way, where we would have now this minus 1/2 cosine 2x dx. And so our final answer would be the 1/2 x and then a minus 1/4 sine of 2x plus c. The reason why I think these are both worth our time in the video is because you'll see these a lot. The integral of sine squared and cosine squared will come up, and knowing what the result is without having to go through each each tedious step every single time will save yourself a lot of time. It's much like now we're to the point of quickly knowing that the integral of e to the 2x dx is going to be the 1/2 e to the 2x plus c. Again, we've done that so often that we know it's a u sub, we know what happens, and so we can go straight from one to the other. This is kind of one of those things where you'll see these enough to where once you start seeing them, being able to go straight to the actual integral is probably something worth spending some time on. Okay, so as we take a look at our next example, you'll see that things obviously ratchet up a little bit here. This is the type of problem you'll expect to see a lot of in this section, where we have these trig functions, but they're raised to higher powers. And it's going to be up to us to manipulate them using identities and whatever else we can to get them in a position to where we can integrate. Okay, that's going to be the goal. Do whatever you can just to get yourself in a place where you can actually then figure out what the integral is. So for most of these trig functions, there are multiple identities you can pick from. Therefore, this section can be a little bit frustrating in selecting maybe the wrong identity and then working the problem and really not making any progress. So just be patient. The more of these you do, the easier it's going to be to see what's the correct identity to pick. But for now, again, just be patient. So for this particular one, to get started, I'm actually going to go ahead and use the two identities that I showed you in the last screen. I would split this guy up as 1 minus cosine 2x over 2. That's going to be the identity for sine squared. And the identity then for cosine squared, that's going to be a 1 plus cosine 2x over 2. But since it's to the 4th power, that's got to be squared itself. Okay, so this is a cosine squared identity. Cosine squared would give us cosine to the 4th. All right, so from here, what I'm going to do is I'm going to pull out the constant. I'll be able to pull out a 1/8, and I'll have a 1 minus cosine 2x times a 1 plus cosine 2x times a 1 plus cosine 2x dx. Okay, so the 1/8 comes out from the 1/2 here. Since this is squared, that's going to be a 1/4. And then I expanded these out completely. All right, so the next thing then, I'll keep my 1/8 there. And I'm going to multiply these two things together. When I do this, this gives me my 1 minus cosine squared. So 1 minus cosine squared, and this will be 1 minus cosine squared of 2x. And then I have this 1 plus cosine 2x dx left over. All right, so from here, 1 minus cosine squared, well, we know that that's sine squared. And that's going to be, again, sine squared of 2x times 1 plus cosine 2x. And then I feel like we're in a really good spot here. I feel like we're real close to being able to integrate. So what I'll do is I'll take this sine squared and I'm going to distribute it to this term and to this term. By doing that, I think we are then able to go ahead and fully integrate. So that's going to be a 1/8 integral sine squared of 2x dx plus a 1/8 integral sine squared 2x times cosine 2x dx. All right, so I think we're in a good spot. This guy is very similar to what we saw on the last screen. So I should be able to go straight from here down into my actual integral. If you feel more comfortable using the other identity and working it out step by step, by all means feel free. And this one over here is just going to be a nice u sub. So for this one, I would let u equal sine of 2x. Our du would equal 2 cosine 2x dx. And then we would just divide the 2 off to the other side and have a perfect fit. All right, so for that first term, we're going to have our 1/16 x minus 1/4 sine of 4x. And remember, the reason is, if we take a look at this guy right here, we move over to the side, the identity here that we would be using would be this 1 minus cosine 4x over 2. Because it's a 2x to start, this would have to be a 4x. Once I take that 4x into consideration as I split this up, that's going to give you this 1/4 right here with sine 4x. Okay, so again, if you need to take a second, pause the video, take this integral using this identity off to the side, integrate, you should end up with this guy right here. The 1/2 gives us the 1/16 right there. And then this guy right here, this is just going to be a basic u sub as we discussed. And when I go ahead and do that, that's going to give me a plus 1/16, the integral u squared du. And then when all's said and done, I'll go ahead and distribute that 16 in there. That's going to be a plus 1/48 sine cubed of 2x plus c for our final answer. So as you look back on this integral, again, it's one of those things where coming up with this on your own will take a little bit of practice, and you'll probably go down some dead ends, but having done that, you'll learn what works, what doesn't work a lot of times, and you'll consistently get better at it. But what I would encourage you to do is kind of just circle back on this now and review what we did here, taking advantage of the identities, expanding it out with some more identities, and then getting ourselves in a position right here where we recognize that we're able to integrate both of these separately from past experiences. And from there, then it just turns into a little bit of algebra, a little bit of trig, and then you're finished. Okay, so for this integral of secant of x, you might have seen this earlier in the course, but I'd like to go ahead and spend a little time on the video with it, since it is one that is going to come up quite a bit moving forward. So for this one, because we don't really know what the integral of secant is, we're going to have to figure out a way to manipulate it. And if you've remembered, if you read the textbook, you can see what we would do is multiply top and bottom by secant x plus tangent x. And again, it seems like a bit of a stretch, but once you do enough of these, you'll start to be able to recognize very efficient ways to get what you need. And so when we do this, in the numerator, that's going to be a secant squared x plus secant x tangent x. And in the denominator, we would have this secant x plus tangent x. And so from here, we went ahead and we let u equal the secant x plus tangent x. And when we do this now, the du for secant would be secant x tangent x. And then the derivative of tangent would be that secant squared of x. We don't want to forget our dx again. So it's a perfect match for what we have up here in our numerator. So when all said and done, we have nothing more than 1 over u du, which turns into the natural log of the absolute value of u, which is secant x plus tangent x plus c. Much like those cosines and sine squares from the beginning of the video, the integral of secant's one that shows up quite a bit as well. So it's probably one that you'll want to remember, that this integral is going to go straight off into this guy to save yourself a little bit of time, even though you certainly could do all of this each time. I would also encourage you to spend a little time, maybe pause the video now and do cosecant, which is very similar. You have to multiply by something like I did here, and then you would get the result for the integral of cosecant in a similar way. Okay, so now we'll take a look at the integral for secant cubed. And this is one that comes up quite a bit, surprisingly. And so as we look at this and how we want to get started, we're actually going to split this apart into secant squared of x and secant of x dx. And we're going to integrate this by parts. So we need a u and we need a dv. Again, we select our u and our dv based upon what's easiest to differentiate and what's easiest to integrate. And since we're dealing with both trig functions, then we're going to need to make our decision solely based upon that idea. What's easiest to integrate, what's easiest to differentiate. So knowing that, that's going to be our secant of x, right here, secant of x. And then this would be our secant squared of x dx. Okay, again, what's easiest to differentiate? Well, secant goes to secant x tangent x dx, and that v gives us tangent x all by itself. All right, so as we put this stuff together, we now have uv minus the integral of v du. So for us, it's going to be secant x tangent x minus the integral of secant x times tangent squared x dx. All right, so now we're up to the point where we need to figure out how to integrate this. Well, conveniently, tangent squared has an identity that involves secants. So it looks like we're able to get everything down at least into secants. So secant x tangent x minus the integral secant x, and then the tangent squared is going to be secant squared x minus 1. And from here, I'll go ahead now and distribute the secant in there. I'm also going to distribute the negative. So you'll see the first one be negative, and then you'll see the second one be positive. So we'll have our secant x tangent x minus the integral of secant cubed of x dx plus the integral of secant of x dx. So now, where do we go from here? Well, this is one that we actually just came up with. So that's one we can go directly into. This guy, however, isn't. But if you look back to the original, that's what we have. So this is one of our integration, circulating integration by parts. So the integral of secant cubed of x dx is equal to this. And I'll go ahead and I'll add a secant cubed x dx to both sides. So on the left, that's going to give me 2 of these integral of secant cubed x is dx. And on the right, I'm going to have this secant x tangent x, and then plus this guy here. And that we found out to be the natural log of the absolute value, secant x plus tangent x. And finally, if you'll remember, we want to get this integral all by itself, so I'm going to multiply both sides by 1/2. And that gives us then, for our final answer, for the integral of secant cubed x dx, a 1/2 secant x tangent x plus 1/2 natural log absolute value secant x plus tangent x. And once again, don't want to make it this far without that plus c at the end. And so there you go. So once again, we start as a trig power integral. We have to be a little bit clever in our approach by dividing it like this and then applying the integration by parts technique. But at the end of the day, you'll find out that it circulates, add over what you don't want, and then divide off the constant, and you'll have your result.